we'll first start to recall you a bit where we were before the break and the past lecture on spins. Yes, so what was the general setting? We were considering parameter estimation, right? So if you remember, we had objects like, well, in our model, we had some probe, or probes, some system, some physical system, which is a probe, right? Then it used to interact with some field, for example, which encodes a parameter, yes? So then we have something like a parametric curve, right? So this state, the final state of the probe system, it depends on the parameter which we want to estimate. All right. So this rho b is some curve in a space of possible physical states, and then we have seen that for the estimation of b, if we construct these unbiased estimators, actually it's also true for biased estimators. But the very important thing is the quantum Fisher information of the state. So the quantum Fisher information was quantum Fisher information. It's the property of the state on the neighborhood of some point, right? So this is the state for B here. Then it only depends actually on the state and its derivative, yes? And we've seen that actually one way to see it is that this tells us how fast the fidelity between the state drops. So the fidelity between the state rho at B and the neighboring state B plus BB, right? And this fidelity, it's like a cosine of the angle. So it only decays quadratically. There is no linear term here. Yeah, of course, you need the limit here. So this is the limit when dB goes to 0. Yeah? So this Fisher information is pretty important because then we have, for example, the Kramer-Rao bound, which will tell us that the mean squared error. So let me recall this. Here maybe Kramer-Rao bound. Kramer-Rao bound. Yes, this will tell us that if you want to estimate B, so we construct an estimator, and then the error of this estimator, so which is like expected value of this estimator minus the true value squared, right? This cannot exceed the quantity which is just 1 over the Fisher information of this state, or actually of the parametric curve, of the neighborhood of the state on the curve, right? This is what the Fisher information depends on. And maybe the last reminder is that, well, this thing is not easy to compute, as you imagine, and then we've seen that there is this SLD formula. Yeah? So we also show that to compute this quantity, the susceptibility of the fidelity, we can just solve the SLD equation. So the SLD equation, it was something like, so if we have, right, we have the state rho b here, and kind of here we have the derivative with respect to the parameter, yes? So just small deviation of the state around on the curve. And then we can just define this SLD to be 1/2 L rho plus rho L equal to rho dot, yes? And if we find this, so if we solve this equation, which is in principle linear in the density operator and the derivative, so I think you did it for qubits in the exercises, yes? Then the Fisher information will just be given by, if I remember correctly, yeah, it's a trace of L times rho. But so this is very useful too. So this is kind of the things we've seen the week before the break. Right? Let me check that I didn't forget any factors of 2 because this could well happen. Yeah, it looks like it's correct. So first thing I would like to show you that there is actually, even in some cases, even this formula can be simplified because we can explicitly find this SLD. So I think we can just do it as a warm-up. Right? So I also can warm up a bit doing computation. Then we'll continue, and actually what we will discuss today is we will, in the exercises you've seen some very practical situations where you have like a qubit sensor and some noise, right? And then you see what is the optimal time. Today we'll just consider a very ideal situation where there is no noise, there is just basically just the field, so the Hamiltonian which encodes the parameter on the state. But however, we'll consider a situation where there are many probes. So the probe is not just single qubit, right, or a single system, but there are actually many systems in the probe. And then we will see which kind of states are useful, most useful to estimate, right? And we'll see if some like having some generally quantum state, like entangled state, helps in estimation. Actually, this is really the big thing because it helps enormously. And that's why kind of this quantum metrology field, I guess, attracted a lot of attention originally. Yes, so this was just the reminder. So let's start with the first part. The first part is a little bit disconnected from the rest, but it's a very useful formula we will derive. So let's call it warm-up. Warm-up, okay. This is recording, good. So the reminder, the warm-up, it will be so we'll consider a particular situation now where we have the same story. So we have our state here, row, and it interacts with B, right? And then we get row of B. However, we'll assume again now explicitly, as we usually do, that the encoding here is a Hamiltonian. So in other words, this row of B, right, is just given by the dynamics which is given by the Schrodinger equation, right? Minus I B. So it's just like a channel, there is no time, we fix the time. H and rho IBH, right? Where so this thing here is just a unitary, the usual unitary transformation. UB is minus IBH, right? So in other words, this thing is just UB rho 0, the original state, UB. So the curve in the space of states is just generated with this unitary transformation, right? Very good. So now actually what I want to show you is that there is a simple formula that allows you to find the efficient information of the state, and also the SLD. So how do we do it? Well, first thing is that we will actually do the same trick as we already discussed a couple of times, is that for the computation, sometimes it's inconvenient that the rho is not invertible. So of course, like a pure state, it only has one non-zero eigenvalue, right, which is 1, and the others are 0. So actually what we will do is we'll consider another operator, which is rho bar, and rho bar of D, and this is just rho B, and we add some small epsilon identity. Yes, so this is not necessarily normalized, but in the end, we'll just take the limit epsilon goes to 0, right? And then we'll continue to recover all the formulas that we have with this thing, which is invertible and which has no 0 eigenvalues. Right here, the smallest eigenvalue is epsilon. All right, so let's now solve the. So given the state, let's now solve the SLD equation. Well, first, is that what's nice about the unitary equation is that we can very simply find the derivative, right? So rho B dot, right? This is just we take the UB, rho 0 UB dagger. So this is our curve. Then we derive it, and of course you just see that you get. So once you have the derivative on the first unitary, and then on the second. So from the first, you just make the minus I H fall. So we have minus I H rho B, yes. And on the other hand, so on the other side, it's with a plus sign. So we have plus rho B times IH. Okay, this is a very kind of compact expression. In other words, we just said that this derivative of the state, it's minus I and the commutator of H and rho B. And obviously, you see that if you just add this identity here, nothing changes. So let me just write it down here in the corner. So we have a rho of B which is equal to UB rho 0 UB dagger, right? And rho B dot is equal to minus I in the commutator of H with the state itself, yes? And then we had this continuation to invertible states. Good. So, very good. Now let's just look at the SLD equation. The SLD equation, remember, it's just given by the SLD equation. So SLD is symmetric logarithmic derivative, just too long to say so. Equation. We get like 1/2 L of rho plus, that's run, rho L equals to rho dot. Of course, there is a B here everywhere, right? We will solve it for our rho bar with a small identity added. Actually, well, I just give you the solution. With a simple way, just check that it's true. So we can actually formally write a solution the following way. We just get 2 integral from 0 to infinity, and then we take here minus alpha rho B dot minus alpha rho B d alpha. Okay, so just an integral over scalar parameter on this real half real line. How do we check it? Well, easy. No, let's just put it in. So let's take this expression and see what we get. We have 1/2 L rho plus rho L. This is equal to, so I just see the 2 cancel the integral, so I just get integral of 0 to infinity. First I have like this expression here, minus alpha rho L. I drop the d because it's just too long to write. Minus alpha rho times rho. Okay. And then we have the same thing but with rho on the other side. So this is plus rho minus epsilon rho dot. All right, d alpha. This is the integral we get. Okay, for this thing. But now you see that basically this thing we get here is precisely the derivative of this quantity here with respect to alpha. Because if you derive with alpha, so you see, so okay, let me just write it down. So this is d over d alpha. The derivative is minus sign of, okay, it's minus this quantity, minus alpha rho dot minus alpha rho. Right? Do you see this? No, maybe not very well. Can you see something?
Yeah, it's a little bit small though.
A bit small. Maybe, yeah, it's kind of, maybe the table is a bit further away than. Let me try quickly. That's maybe better.
Yeah, better. Thanks.
I'll just the focus here on the camera. Oh, no, it's still okay. Yeah, very good. Yes, so yeah, you agree that this is, so if you derive this expression in the brackets here and the parentheses with respect to alpha, we just make once the rho falls on the left, once it falls on the right, so we get precisely the same thing, and with a minus sign, right? Because well, so this is just the integral of the derivative. So in other words, we just get that this integral is just minus e minus alpha rho dot minus alpha rho taken at 0 and infinity. Okay. Let me just write it down so I cancel this. Yes, let's just maybe do it here quickly. Another color. So I just take this expression here and, well, so at infinity, because rho now doesn't have 0 eigenvalues, so it only has positive eigenvalues. At infinity, this operator here, so well, it's just identity, right? So because it's minus, is identity? No, it's actually 0, right? Because it's, at the end, the thing is exponential of minus alpha something non-zero, right? So everything it just has 0 on the diagonal, exponential of positive quantity with alpha going to infinity. So at 0 it's 0, right? So no, at infinity it's 0, right? So we get minus 0 minus its value at 0, and its value at 0 just when we set alpha to 0, we'll just get identity here. So we get minus rho dot. Yes, in other words, this thing is just given by rho dot, right? So that's the point. So this kind of expression allows you to compute the SLD explicitly. Let me just recall it because I erased it. So what we found is that once we have this invertible rho, we can formally write the SLD here. It's given by 2 times 0 to infinity of exponential of minus alpha rho dot minus alpha rho. So this integral. Okay. Still, this is not the end yet because now I want to express it in the basis where rho is diagonal. So we use the spectral decomposition of rho now, and we will just get the expression of the thing. So how do we get it? Well, let's, yeah, well, it's not difficult. We just take the spectral decomposition. So rho, you know, it's just a density matrix, so it's emission, everything, well, the usual thing. We'll just write it as pk projector on k. Yes, so this is the spectral decomposition of rho. And this allows now directly to express this thing in an even better form. Because we get now L is 2 times integral of, you see, this means that exponential, so if from this expression directly we get that exponential, right now, maybe here, still not used to this small black word. So yes, so from this we just get E minus alpha rho. Yeah, it's just going on the same basis, obviously, so this is just E minus sum of K. E minus pk alpha kk, right? Just take the function of the eigenvalue. And then L is simply 2 times integral of, now I have 2 sums because we have this thing appearing twice. and we have sum of k and L of exponential of minus pk coming from here. Or let's put it like this, minus alpha, right? Pk. Yeah, we just write it first like this, k rho dot L exponential of minus PL alpha. All right, I just plugged in the expression here. Yeah, well, this can be further simplified because we just integrate over the same variable. So we get sum of KL of KL, our operator part. Then we have just the value of rho dot on these vectors, and the integral of 0 to infinity of e to the minus alpha pk plus pl d alpha. Okay, but this integral we can just solve it, and this thing is what again? Yeah, I guess we get 1 over pk plus pl from here, right? Because when we integrate, we just have to divide by the sum here with a minus sign, but then again at infinity it gives 0, and only at 0 it gives something. So we get check. We get that the SLD can be nicely written in this form as KL times K rho dot. Oh, I'll just repeat it again. Divided by PK plus PL. So once we have our spectral decomposition of rho, which in principle is not so hard to compute, we can directly get this LD. Yes. One more thing. So let me just write it down again. So we get in other words, from this expression now I can forget it, right? I don't need it anymore because I will just use this one. We'll use this one, and this one tells me that did I forget the 2 here? Yeah. Well, let me just check it. So sum of KL times K rho dot L divided by PK plus PL. Okay. Let me check if there is a 2. Might have forgotten it, I guess I did. Yes, obviously there was a 2 in front. Huh? Nice. So finally, we just take the rho prime now, like rho prime, and just write it in this basis again, right? Rho prime obviously given by, and of course the same thing holds here. So we just modify the eigenvalue. So we can, everything we do, we can just think of having a bar here, right? We'll take the limit at the end. So yes, this thing is, we said it's minus I commutator of H with rho. Okay. So this is, in other words, what do we get here? We get, we'll get minus I H. I'll just take the first part. Minus I H sum of K. PK minus or plus I sum of K. Or let me take L here as the index, L H. Okay, now I'll just do the usual trick, so I'll just plug the identity here, sum of L on the right side, and here we'll plug the identity expressed with the K index, yes? And then we can again get the nice expression in the KL, in the basis, it's eigenbasis of rho. So here we just get, you see, so if you have L here on the left, so we'll get sum of KL of minus I and L acting on H. So basically we get LK and LH. Okay, yes, from this part here. And from the other one we get plus I. Sorry, there is also a P. So of course there's a PK here. Should forget. Okay. And here we get PL. Same thing, LK and LH. Okay, correct? PL, yes, same thing. Okay, so in other words, rho prime also get a simple expression. This is just given by minus I sum of LK of the operator LK times LHK times CP, so it's PK minus PL, right? All this, good. So finally, since we have this rho prime, we can plug it there. It's not so fast. I'll just write it here again. So we have rho prime is equal to minus I sum of KL, LK, and here we get, let me just write it as HLK, right? This is this matrix entry in the basis where rho is diagonal, PK minus PL. Yes, finally we'll just put it in the SLD formula and get our result. Sum of KL, KL, you see, so K, so the entry KL on the row dagger, also on row dot, sorry, this gives us minus I, and we get, so K is equal to L, so we just have to invert it, sorry. This is A, H, K, L, and P, L minus PK, right, divided by P, K minus PL, okay? So, in summary, we have now a nice expression for the SLD. So, I, sum of KL, H, okay, HKL, times PK minus PL, divided by PK, sorry, there was a plus here, PK plus PL, times was just the pressure part. Okay, good. Finally, we're done. It's quite long actually. I didn't realize it so long to derive this thing. So what can we do now? We see if so. It's a closed expression, right? So you see it just involves actually the weight of the state of rho, actually of rho bar for the moment, and just the matrix, the Hamiltonian written in the eigenvalues of rho. Okay, so there is nothing to compute. Once you have these things, and you can diagonalize rho, you can just directly express your SLD operator. So it's quite nice. You don't have to solve anything basically once you have the diagonal form of the density matrix. One more thing is that now we can actually take our limit. Okay? We can take our limit for epsilon going to 0. So let's see what happens when we take epsilon going to 0. Okay, and then we can get this expression also for non-invertible things. And you see that what happens here is that if k is equal to L, then this thing is just 0. Okay, but it's particularly problematic if so also if pk is equal to 0. So if we are considering an eigenvalue of rho with an eigenstate of rho with eigenvalue 0, then this denominator here will make a problem. So this limit will not be defined in 0. So actually, first, since this thing is 0 when pk is 0, we just write this thing as a sum of kl. You see, such that k and l are not equal to 0, 0. You agree that by just dropping the terms, because for the terms where not kl but pk and pl, pk and pl is not equal to 0. So we agree that when we take this thing and we actually take a pair of values where pk and pl is equal to 0, we do get 0 here on top and 0 here. So actually it is 0, right? So first, so here we have 2 epsilon, here we have 0, right? So before taking the limit, it's clear that it's 0. So we can just drop these values. But when we take the limit, it will be a problem. So we first drop this term from the sum. So we just write the sum like this. And then you see we just get our same expression, HKL of pk minus pl. So this will actually some kind of, here we have the bar state, right? Because we did everything for the invertible operator. KL, right? And then, but once we drop it once we remove these terms from thing, there is no terms which are problematic anymore, and we've taken the limit epsilon going to 0. This thing is always finite because there is no, actually removed here all the eigenvalues where pk was 0. So here we have something finite always. So now taking the limit, another problem. So we can just remove the thing, and we get our nice expression. So actually, the limit was just to take care of this nasty eigenvalue zeros here. Yeah, so this is our expression, which we get. So maybe I guess we'll use it in the exercise to compute some, to see how good it is. One more thing is that we can also just take it now. I will not show it because it's just, so once we have the SLD formula and we have the rho dot, what we can do is just compute the Fisher information. Yeah, so it's the Fisher information then of rho b. Again, it's just a trace of rho dot times L. Well, I mean, you just multiply the two and trace them out. Let me just give you the result. This is kind of the formula you always see if you read a paper on Fisher information. It's like this very often. So you just get here, when we do this, we get the following thing. 2 sum of this k and l such that pk and pl are not equal to 0, 0, 0, so they're not together 0, and then pk minus pl square, pk plus pl, and here we have khlh squared. Okay? So, I mean, of course, it's in the note, so you don't have to remember it now. But that's a very convenient formula which allows you to compute the Fisher information in many cases quite fast. All right, so it took a bit longer than expected, but was more than a warm up. But okay, nice. We have a nice formula. Any questions for this? Was it clear?
Clear.
Good. So okay, now let's go to real things now. So now, actually, this lecture I called it quantum metrology with many body systems. Quantum metrology with many body systems. Many body systems. All right. So what is the promise again is now we look at. Now we have an individual probe, right? It's a quantum system which is described by some Hilbert space HP. Typically, we can think of it as a qubit, right, for all our examples, just to simplify our lives. But now we have let's say that we have many probes. Okay, so if each probe is kind of described by the state in HP, then we have all these many probes, which will all undergo the estimation, right? So the total system, which is our sensor, is now in H, the Hilbert space, which is the tensor product of all this. Probes, yes, to the n. So we say there is n probes. There are always n big N probes. Okay, and we do the same thing. Now it will send some magnetic, some field or some signal, and then just get a global state and try to estimate the parameter from this global state. Okay. One thing we will consider actually is transverse interactions. This is important. What does it mean, transverse interactions? It means that the encoding here, so we say that now for each individual probe, actually the probes are all kind of similar. So for individual probes, Hamiltonian, the interaction Hamiltonian rest, so it's a unitary encoding, right? And the interaction is just given by E minus time, so the usual one. It's an Hamiltonian interaction, right? Do you see it well? This is important. So each probe here interacts with Hamiltonian HI with the field. So we just get kind of this unitary signal acting on the probe. Yes, but then of course, since each field interacts like this, the global unitary transformation, general, let's put it like this. This is just a tensor product of all the small unitary transformations for each one. Yes, so E equals from 1 to n. So each sensor here sees exactly the same Hamiltonian, except the label I, which tells us where it acts. And then, of course, we can just, since all these Hamiltonians acting on different probes in commute, right? This is just a tensor product of exponential. So in other words, this is just minus IT B, and here we have a sum of small Hamiltonians equal to 1 to n. Okay. Good. So if the small Hamiltonian for a probe now was HI, Yes, this is Hamiltonian, which describes the interaction of the small single probes, and for the big system, the collective one, H is just the sum of HI. Is it clear what I'm writing here? That's important. Yes, so basically we just, in other words, is it clear? So it's a bit connected to, so it's actually pretty much connected to the collective spin things you've seen. And so this is just a collective operator. You're fine with this, right?
Yeah, it's just there's a difference, right, between the dimension of the Hilbert space of the entire system and the actual Hilbert space. I don't know if that makes sense, because the Hilbert space is just the sum of the little parts, and the dimension of the Hilbert space is the tensor product of the little dimensions.
Yeah. Yes.
Okay.
Right. Yeah. So I mean, maybe what you're talking about here is what you also seen last week. That of course, if you just look on the dimension of the big thing, right? So let's say for qubit, right? Qubit is just 2 times n, right? Yes. You just take a basis for each one, and the global basis is defined by just the product of all possible basis vectors. So there's 2 to the n combination, or in general there will be d to the n combination, right? If each local space is dimension d. But then when we talk about this symmetric states, right? This will be much fewer of them. It will be just n. And actually, yes, it will only work. So this moment, all these things they can be defined on the whole space. But yes, we actually will only consider symmetric states, so we will actually work in a small dimension. Yes, so indeed we will only a small part of this global Hilbert space will be relevant for us. That's true.
Okay.
So let me just summarize it again. So with some pictures. Yes, so we have just a single probe here. It just interacts with this, with the Hamiltonian, with B times HI, right? Hamiltonian. This is the system I, okay? And then we're going to state out where parameter is encoding. But now we just consider the same thing, but where many things happen in parallel, right? So all of them interact with the same Hamiltonian. Well, acting in different systems. So actually, this is equivalent to say that it's just a global Hamiltonian H, which is equal to so BH equal to sum B sum of I HI acting on this global system, all right? Just the same thing. Of course, when you write, when you write HI acts on the global system, what we really mean, right? So so it's just a kind of a physicist image. Mathematically, we will say that HI, we cannot write a thing. What we have to write is like identity on the first system, tensor product identities everywhere, right? This is actually what we mean by HI. So you agree with this? So this is actually how HI is supposed to act on the global Hilbert space. It kind of trivially acts on all of them and only rotates this one. But of course, it's kind of explicit when we know what we're talking about when we say HI acts on I system. Good? Yes. So that's the point. And yes, so when you, in the exercises today, you've seen at the end there was an exercise on kind of sensing with the spin coherent state. This was a similar situation there, right? There was each individual spin 1/2 or qubit was rotating with the same Hamiltonian, and there was a collective S. Or was it like this? Maybe it was not written like this. Good. So that's the point. So now the question is, let's ask our first question. The following one is, well, let's just consider the simplest situation. Okay, so this is our H equal to sum over HI here. And in principle, we can also do a global measurement of that. So first thing will be to consider product states. So let's say that we start with a product state. What's time? Yeah, that's fine. Well, maybe before the product states, let us just look on an individual system again. So let's just look on an individual system and discuss the role of time without noise. So first thing is that what is the role of time? Role of interaction time. Interaction time. So you remember in the exercises we've seen kind of a situation where we had this sigma z Hamiltonian, right, acting on the sensor, on the qubit, and on top of it there was some noise. And we've seen that kind of the result always an optimal time for which you let the system interact, where the Fisher information is maximal, and then you measure it out and you reconstruct the estimation. But now we're dealing with an ideal situation. So in the ideal situation, there is no noise, and actually there is no optimal time. So basically, for the fish information, the best is just to run it forever. And well, we can easily see this because you know that. So our encoding for a single qubit, right? Encoding is given by this. So you have our the state. Let's say let's say this is the original state. So initial state is psi 0, right? And then I have the final state. So the state at time t is just psi t b, yes, and this is equal to e minus I t b h. This is our interaction between psi 0. Okay. Yes. So in other words, we can just we will just write it as, let me write it like this, minus I b, which is the parameter of the sense, times th. Okay. So here b is a parameter and th is actually the generator of the transformation. So remember, if you look at the Fisher information of this state here, psi as a function of b, right? So let's write like this, psi as a function of b, but of course t is a parameter here. Then remember the Fisher information of the state of psi of b, right? For the pure state, it's just the variance of the estimator. Good. So this is just the variance on the state, actually on psi 0 because it all commutes. The variance of psi 0 on the generator, and the generator here is th. Yes, because t you can absorb the interaction time in the Hamiltonian here from the perspective of this encoding. Sorry, on the state psi 0 of th. So of course this variance, right? I mean, we could just compute it quickly, and you see that this is just th square on the state minus th square, the absolute value square. So in other words, this is just t square, which is the variance of on the same state of h. Yes. So what does it mean? It means that the time really doesn't play any non-trivial role now without the noise, because at the end the Fisher information is just the Fisher information for t equal 1, right? So setting, forgetting the t here is just like setting t equal 1. And in other words, so yeah, so there is no need to kind of treat everything for different times. We can just say, okay, let's just fix the time to be 1, and the conclusions will be true. If the interaction time is different, we just know that at the end the Fisher information is what we compute for t equal 1 times square. And actually, I mean, maybe let's just skip it now, but for example, the optimal measurement is also trivially related for different times. Yes. So really, once we solve the problem with t equal 1, we solve all the problem. In the case without noise. Of course, in the case with noise, actually time plays an important role and a non-trivial role. And we come back to this in a couple of lectures where we will discuss about noise in this parameter estimation, right? Have like general discussion. But so far we just consider the ideal situation. So we just fix t equal 1. And then our encoding ub is equal by this simply minus I b times this collective Hamiltonian. Yes. This is what the field imprints. This is an interior transformation which the interaction with the field imprints on the state of the probes, of the probes. Yes. So that was the point of time. Yeah, we have still some more time. So let me just so let's start with considering the product states. And again, first let's just consider a single probe. So a single probe. Well, single probe is what we just wrote. So for a single probe, we have the Hamiltonian hi, right? Null Hamiltonian. And the state, the final state, psi b, is just equal to minus I hi times the field b, right? On the original state. And what do we know? We know that the Fisher information of the state, because it's pure, is just given by the variance of this Hamiltonian. Just given by the variance on the state psi 0 of our Hamiltonian hi. Yes. So now I would like just to ask a question. It's simple to see. What is the best state to use? No, sorry. Actually, there was a factor of 4. I don't remember this. didn't correct me. So it's the Fisher is related to the variance for two states, but not just directly. There is a factor between them. So okay, can we now? That's a question we're going to solve now. What is the state what is a pure state which has the maximal variance or the maximal Fisher information, given that we know this operator hi, the Hamiltonian? What do you think? Any idea? Well, okay, let me just so to do this way again, what we do is we go in a basis. So hi again is some Hermitian operator. So there is a basis in which it's diagonal. Yes. So let us define now the external eigenvalue. There is like the smallest, so we'll assume it's bounded. The smallest eigenvalue is just given by something like yeah, let's call it like S mean, right? S mean, some number, and then there are other eigenvalues. So in principle, it's just a big matrix. But then there is a maximal eigenvalue. The maximal eigenvalue we call it S max, but we'll just express S max as S mean plus some delta. Okay, right? Good. So far so good. So actually, I can now let us write it in a bit a different way. And now we will write it. So we'll just same thing, but just to write it the following way. We have we add a constant to all these eigenvalues. So let me shift all the eigenvalues. So we'll just so let me define a new operator now gi. Okay, no. You can just write following. So let's say hi is equal to gi, some other matrix or operator, plus delta over 2 times identity. Okay. So in other words, what I want here is just I just want to find the operator gi where all the eigenvalues are shifted by this value. But we see obviously that then gi is equal to so what do we get here? We get this minus, so we get S mean. No, sorry, that's not what I want. Sorry, guys. No, precisely, I want actually to remove this thing. So I want to write it as hi. So yeah, I'll just write what I want. So actually I want to write an operator the gi, which is like this, minus delta over 2, then some numbers here, and then delta over 2. Because I know that the difference between the extremal ones is just delta. So I can always shift the constant from, I can subtract some identity from this and get this operator. And then of course I know that, so this is just gi, plus I have to add here what is missing. So what is missing is plus delta over 2 plus S mean, right? Is it correct? So yeah, let's check for this one. Yes, gi. So we just get S mean, and for the S max we also get delta over 2 plus delta over 2. So delta plus S mean. Yes. So we just basically what I did is just we decompose this operator h in such a way that in an operator which has an extremal value minus delta over 2 and the other extremal value delta over 2 and the constant. So right, this is not the number, it's times identity. Good. Sorry, I messed up a bit with logic, but yes, that's the idea. Now, why am I doing this? Because if you now write the encoding UB, this is hi times b, right? And this is if you write this formula, this is minus IB gi times minus this thing here, minus I delta over 2 plus S mean times identity. But of course, so this is just a number. Yeah? So this is just a scalar. The identity, you can forget about it. And clearly, this just gives a global phase on the state at the end, and it doesn't have any meaning, right? So we can forget about this phase. It doesn't have a physical meaning. All this to say that instead of considering a general operator like this, we can always just shift the Hamiltonian in such a way that we have this operator h gi we can replace hi with gi, where gi is just has symmetric, for gi the external eigenvalues are symmetric around 0. Yes. So we can just now, without loss of generality, because this constant factor doesn't matter for estimation, we will just assume that hi is of the form like this. Good. 3 or 2. Yep. Okay. So very well. Just finish with this extremal state, this optimal state. So yes. So like I said, this is hi now. So the question now is, what is the state? So find the state. So to find the state which has maximal Fisher information now for this Hamiltonian, we need to find the state which has maximal variance for this Hamiltonian. Find psi I with maximal variance. Maximal variance. Okay. Well, and actually, maybe we want to take a guess now. No, well, okay. So one thing we need still is just to define the eigenvalues, the eigenstates which corresponds to these eigenvalues. So let us call this eigenstates S mean. S mean is the one where when we act with hi, we get minus delta over 2 S mean, right? And hi S max, the other external eigenvalue is the other one, right? S max. So you see what happens here. So I just define the eigenvalues here which correspond to this eigenvalue and to this eigenvalue. Well, now what I suggest is that the state psi opt, so the state of maximal variance, is just equals to the position of this extremal eigenvalues, which is actually so S mean plus some phase factor here, which is arbitrary, S max. Yes. This is similar to, well, actually it's the same thing. So maximal variance, it's a classical problem, right? We just have a spectrum and we need to find a distribution which has the maximal variance, right, on the line. So clearly just equal peaks on the extremities, and we can show it. Yes, so let's first compute the variance of the state. We compute the variance of the state, and so variance of psi opt, this is equal to h, so that's h square, sorry, h small h square minus h square. So what do we have here? Well, let's start with this guy maybe. H square. Let's start with the second one. This is we get 1 over 2 S mean plus minus I5 S max times minus delta over 2 delta over 2 something here. Something here is not relevant because we only have the external eigenvalues here. S max S mean plus, well, EI5 S mean, and clearly you see that we just get S mean, so we get squared. So this is h squared. So we have this thing squared. So square just removes the sign, right? Yes. So we get 1/2 S mean over this. So in other words, we have delta over 2 squared. Yes. So h squared is this. Delta over 2 squared. And h, well, again, because now what's nice with this Hamiltonian, that we shifted the eigenvalues to a symmetric, is that the h will be 0. Yes, so S mean plus I5 S max times this thing minus delta over 2. Delta over 2, 1/2 here. Well, you see that S mean gives minus delta over 2 and S max gives plus delta over 2. So this is 0. Yeah. So in other words, the variance is given by delta square over 4. One last thing is, let's show that this is indeed the maximal variance. Yes. Want to show that this is the maximal variance? Well, for this we just consider in general variance for any state. So variance for an arbitrary state, right? It's h square minus h on some arbitrary state phi. But of course, this variance is, since this thing we just remove it, so it's smaller or equal than just h square over phi. Yes, and this thing is precisely given by delta over 2 square, delta over 2 square over this phi. And clearly, you know, the maximal eigenvalue is this thing here, right? So clearly, we see that indeed we cannot exceed this value. So, in other words, what's the conclusion now from all the story? Is that we found for a single probe, right? For a single probe, we found that indeed this is the best state. This is the optimal state. Optimal state with quantum Fisher information is given by 4 times the variance, if you remember, of h, and this is equal by simply delta squared. Okay. And I think we can take a break now, right? Unless you have questions. No?
Yeah, just on the relative phase of the optimal state. I don't really get it why that would be arbitrary. It should be null. It shouldn't have any relative phase, or why does it have a relative phase in the
It's not a relative phase. No, that's the point. It's a global phase. It's not relative to anything now. So right. So I mean, just so you see. So the point is that now we're talking is pure states. So right. So we have phi, and then we have psi d with some phase here, right? After our interaction, then of course this factor is not important because this is not a physical factor. It's not relative. It's just like a global phase, right? Because even if you go to density matrix, right? Formula, then we just get psi, and then here you see we get just this phase just disappears, right?
Correct. Yeah.
So that was the point. So this global phase factor, which actually kind of depending on how you shift your Hamiltonian, it actually is there, but it doesn't have a physical role. So we can always shift to this Hamiltonian where this factor disappeared for the state. It also depends which state you use. Okay? That was the point. So this identity we can always decompose it. We can always kind of remove it. It actually corresponds to sort of say, usually we say that like a Hamiltonian radius energy reference doesn't matter. You can shift it arbitrarily.
Yeah.
Because it gives the same. It gives like a non-physical global phase factor. Yeah, that was the point. Yes. So, well, let's take a break. Now what we are going to do is we found the optimal state for a given Hamiltonian. We found the optimal state. We'll just now see if we have a product of the states, what we get as a Fisher information. And finally, we will at the end, the second step will be to look at now the optimal state of the global Hilbert space, right? And what is the Fisher information there? And we'll see that there is a factor of n difference. But yes, but yeah, this is, so let's take a break now and then we continue after the break. Good.